So last talk, and there's been enough talk about NVMe-over-Fabrics, I think, in this last couple of days, and hopefully this will give you some practical overview of how people are trying to use NVMe-over-Fabrics and what are the advantages. So I call it low overhead flash disaggregation. That's one of the use cases for an NVMe-over-Fabrics enabled architecture. So let's get to it. Standard disclaimer, this is Samsung. We are very experimental. This particular talk has a lot of data and things like that. We don't actually promise that you'll get it, but as an engineer, I think you will. But we'll go from there. First thing, let's just talk about the NVMe SSD quickly. I think everybody in the room should be quite familiar with what the technology does and what the technology has done for storage in particular. So basically, it's a really high. It enables really flash is SSDs are inherently parallel. Flash is inherently parallel. What NVMe technology does is it allows you to use that storage in an extremely parallelizable way. And so you can see today you can buy NVMe SSDs that deliver you 1 million IOPS from a half a dozen companies. You can get NVMe SSDs that are 6 gigabytes per second from a single device. So how do you actually use these devices efficiently is actually the main goal of what I'm talking about. How does it do that? You'll have to look at the NVMe spec. It's got inherently a large number of queues, and each of the queues can talk independently to different channels in the SSD. That's how it is different from SATA and SAS SSDs of the past. And of course, they still sell it gigantic volumes, and we love to sell them. But this is what we think is the next generation of SSDs. So that's the SSD. What's NVMe-over-Fabrics, right? So it's a protocol that enables NVMe to be NVMe operation over an interconnect, whether that be Ethernet, InfiniBand, or so on and so forth. And what that does, and it also shares the same basic NVMe architecture. That means that a lot of the software running on the target and all that, a lot of the drivers are all very, very similar. And the parallelism extends. The parallelism we talked about in the NVMe SSD is extended over to work over the network. That enables really powerful storage technologies, parallelization to happen over the network. And NVMe-over-Fabrics design goal was to impose only about a 10 microsecond latency overhead as you go over the fabric. And it obviously avoids all of the unnecessary protocol translation that happens with SCSI, SAS, and other things if you were to go over the network. So these are primary benefits of NVMe-over-Fabrics. Now how it works is you have a regular CPU, you put in an NVMe-over-Fabrics bridge, it talks over an RDMA-enabled network to a target controller. That is again NVMe. So instead of just running local, now you moved it over to the other side of the network while essentially keeping the benefits of NVMe and also introducing extremely low overhead due to RDMA. So those are the top line, and I think many people have talked about this before me in this particular conference itself. So let's talk about how we would be using NVMe-over-Fabrics in a real world scenario. There are multiple use cases, multiple ways you could use it. One of the more common ways is it could be used as a SAS JBOF. That is, you have an NVMe-over bridge connected to a SAS JBOF. That's one use case. That would replace a lot of the JBOF, SAS JBOF type architectures. The other one is, on the other side, is you could use it to run something like a Hadoop cluster, a distributed set of nodes talking to each other over NVMe-over-Fabrics. And the storage protocol would run over NVMe-over-Fabrics. That's another use case. In this particular talk, I'm going to talk about what I call a disaggregated, just a bunch of flash storage. That's a very common use case, we think, in data centers, and we'll go through some use cases of that. Basically, you have a bunch of compute servers that can talk to a network of flash devices, right? So you could have one or many flash devices connected in a box of some kind, 1U, 2U, and all of these boxes are connected over NVMe-over-Fabrics. So that's sort of the use case we want to talk about. This is really cool because this enables a lot of the data center customers to scale their compute independent of the storage, and this will enable a bunch of things enable a bunch of really good features for storage itself, basically scaling it and so on, and we'll talk about those things too. Currently, NVMe devices are extremely underutilized because we said one device can deliver 3 gigabytes to 6 gigabytes per second of sequential bandwidth. One device can deliver 1 million IOPS. Can applications really use that? Very, very hard. Very, very hard. So if you, in current architecture. So this is an example of running TPCC MySQL. For those who don't know what that is, MySQL is a relational database. TPCC is a classic age-old relational database benchmark released by TPC, Transaction Performance Council. People have been running this for 30 years. So what I'm trying to show is the CPU is you're going to run up, as you run transactions through the database, you're going to use up all your CPU. Your NVMe utilization is going to be about 20%. So you've already maxed out the CPU, and so by providing a really fast storage, you're not going to be able to utilize that. So you might as well just stick a SATA drive there and be happy. So we're going to try to figure out how we can use this NVMe over bandwidth, and the key thing is sharing. How do we share the bandwidth? How do we share the IOPS so that we can efficiently utilize the extremely fast devices that we are building? And we're going to do that with storage disaggregation. What we're going to do, and this is not a new technique, it's people have been doing it for a long time, but there are some specific things that have happened that is going to enable NVMe devices to make storage disaggregation more powerful. So basically, we're going to separate out the compute and storage, and this we're going to do because we now know that networks are getting really fast. We have 100 gigabits today, 400 gigabits coming out soon. We have finally arrived at RDMA that is almost a standard. Two of them, of course, but it's still good. And then we have really, really high density flash. We are talking, at the Flash Memory Summit, they were releasing 32 terabytes to 128 terabytes SSDs. It enables independent resource scaling, so you can scale your CPU computes independent of storage and help you, save money. And the only thing it introduces is an overhead to go over the network, and we want to quantify that and handle that. So that's about the overview of disaggregation. So now we'll talk about the numbers we have. So we'll be using some notations. So first we call data centers have an application layer. So there'll be a separate set of computers running the application, separate set of compute nodes running applications. Applications are TPCC. That's the application that drives the database transactions, or DB bench, like Vishal talked about in the thing before. Then there's a data management layer. That is where we run the database itself. In this case, we will be trying MySQL and RocksDB. And then there's the storage layer that actually does the persistent storage. So that is what is disaggregated. It doesn't do any of the storage. It doesn't do any of the data management functions. It just handles reads and writes and storing that stuff. NVMe disaggregation is much more challenging, because the devices below, what our goal is to utilize, not introduce an additional latency to this already ultra low latency of 90 microseconds that these NVMe SSDs now provide, but also we have to drive it to the maximum IOPS, 1 million IOPS. So while doing that, we want to extract all that, but not introduce any additional latency to the top of the 90 microseconds. If you had SATA devices over there or SAS devices over there, you have a lot of time. It's not really a big problem. You don't have that many IOPS. It's not really that big a problem. But when you put in NVMe devices, it becomes a bigger challenge. So we'll look at three classic cases. The first one is FIO, which is a synthetic benchmark test, which helps us bound our problem in some case. What is the maximum overhead that we will see? It helps us define, it helps us make sure that our system is properly designed, that we are meeting the original design goals of not imposing more than a 10 microsecond overhead on the latency and stuff like that. So that's the point of the first set of results. RocksDB, we just finished a RocksDB talk. It's a very powerful key value store. Key value stores in general are a database or database of choice for big data applications. And NoSQL databases run key value stores in the background. So RocksDB is a really good use case for us to look at. And last, MySQL. I was telling somebody MySQL probably runs most of the databases in the world. All your, Equifax was hacked. It was probably running on MySQL database. I don't know for sure, but it's like MySQL is running everywhere. So we will benchmark MySQL running on a disaggregated store. So first, what's our methodology? What are we doing? So we're going to look at three basic configurations. We're going to look at local, that is we stick the SSD inside directly in the box that we're going to run the application on. Then we're going to stick the SSDs in a remote storage box running NVMe-over-Fabrics with Rocky V2. And then, for sake of completeness, we're going to run it with software iSCSI also. So FIO itself will have three host servers which are running the traffic, and the target server is a single, very powerful quad socket, but it has about 96 CPU cores, and this will be populated with up to 8 drives. I think we're using 3 in most of the cases with NVMe SSDs, and you can see these NVMe SSDs have 750K read IOPS and 3 gigabytes per second of read bandwidth that each SSD can deliver. So we're going to run it and see if we're going to stick the drives in here. Actually, we're going to stick the drives in here, run RocksDB here. That would be the FIO, or that would be the local, and then we'll take it over the network and see what happens. Our configurations are over there. We're trying to just maximize, so queue depths are deep and lots of jobs. So this is the maximum throughput we get. So and it's not for just one point case. We ran like a whole bunch of use cases from 100% read to 100% write with every mix in between. And we have three columns here. The blue is DAS, direct attached storage. The red is NVMe-over-Fabrics, and the green is iSCSI software, iSCSI. And what you see is across the board, NVMe-over-Fabrics throughput doesn't add any tax on it. There is no tax due to NVMe-over-Fabrics on throughput performance of SSDs itself. iSCSI, of course, has a tax.
Is this network loaded or unloaded?
This is unloaded network, right? This network is just running these two things, right?
Was the iSCSI stack optimized with it?
Yeah, it's the best we know. We don't pick
and all that?
Yeah. So it's software though. It's not. It doesn't have the iServe. We're not doing our VMA and things like that. It's software. But you can see, basically what we're trying to show is NVMe-over-Fabrics throughput is same as this. That's the basic point. It doesn't introduce. It's a new technology. It was released last year. There's a lot of doubt. What we're trying to show is, yeah, as far as throughput is concerned, the Fabric software that NVMe Express and all the guys in open source and all the companies working on have done an excellent job trying to get this done. The next one we have to look at is, does it take additional CPU? And the answer is no. It doesn't take a lot of CPU to run the NVMe-over-Fabrics stack on both. This one is on the host side. We'll talk about the target side also. And across the board, you see DAS and NVMe-over-Fabrics tracking pretty closely. Not addition on your client side, not additional overhead due to running the NVMe-over-Fabric stack itself. Of course, we have offloaded with Mellanox's technology, and we can also offload with other companies' technologies. RDMA is the magic underneath that. And software iSCSI, of course, has a big stack to run.
This is for the Fabric space. This is on the client side or on the target?
This is on the client side.
So for all cases, it's on the client side.
I'll show you the host just now. Coming up. Next one, we look at the server. So what he was talking about is we have two things, right? We have the client and we have the target. So I showed that the client doesn't have much overhead. Now we're going to take a look at the target. What's overhead on the target? Because that's the one that's storing all that stuff. Now this is a little bit confusing slide. I'm going to walk you through it. So the black thing, the black is DAS. So if there was no network, that's what we get with about three of our devices. You get about 2 million amps, let's just say that. And there are 3 red bars. The 3 red bars are NVMe-over-Fabrics with different number of cores. The 32 cores, the 16 cores, and the 8 cores. We'll get to the iSCSI later. And the red lines are CPU utilizations. So what we're trying to show is that you can get to 2.2 million, almost 90% of that, with just 8 cores. That means that the target utilization of running the NVMe-over-Fabrics track on the target is extremely low. That's the basic point.
So that looks like 2 million. 2.2 looks like 16.
Yeah, so there, yeah, it's like this one. That's like 2.1. So about 90%. 90%. You get 90% with 8 cores, right? So that's, of course, there's again, RDMA is the magic on the other side too. So there's not RDMA, and so what we're trying to show is it used less CPU. If you look at the same numbers for iSCSI, you have a much higher CPU utilization, and of course, iSCSI can also be optimized with RDMA for sure. But again, there is a protocol translation over there, but here there is none. And we're trying to make sure that NVMe is working good, and that's the basic point of this.
So that 100% is basically, would be 100% that's for the number of cores that you're measuring across the
Yes, 100%.
So
That's right.
The 100% for the 8 core means 8 cores are running.
100%. So that's great. What happens, again, we'll go back to the latency on the client side. What is the latency under load? What happens to latency under load when you're running FIO? So this is just a zoomed in image of that one. So again, you see both the blue line is actually hidden. NVMe-over-Fabrics basically tracks DAS latency with a small overhead of about 10 microseconds or so, right? And that's the basic point. Whether you're looking at average or you're looking at the 95th percentile, it doesn't matter. It tracks the DAS performance with a little bit of gap between them, as was the target when we built the NVMe-over-Fabrics technology. V meaning NVMe Express, all the fine guys out there. And then if you zoom in, and you can see that, yeah, there are some differences, of course, but overall, you're going over a network and all that fun stuff. You're going to get disaggregation. You're going to get all the advantages of taking the sharing that storage. You only introduce a small penalty.
And with the 100% read, or what read write ratio is these?
These are all. This particular one, let me see. I think it's 4K random read. I'm pretty sure this is just 4K random read.
On the right is just a zoom in on the left?
Yes, it is just a zoom in on the left. Just to show, it doesn't show any of the differences, and it's not magic. There are differences. Okay, let's take a look at RocksDB. RocksDB is a persistent key value store. We had a fantastic talk just before us. It's an optimized for flash. It's used in lots of data from many applications out there. We're going to run not the extreme cases. We're going to run two small byte 800 bytes and a slightly larger 10 kilobyte packets through in an 80-20 read-write mix. And we have the same sort of architecture. The benchmark is going to run, in this case, the DB bench. The benchmark and RocksDB, the data management layer, is going to run on 3 nodes. It's going to go over a switch to the disaggregated storage box that's got 3 of our 1725s, which again is the same thing. I told you 750K IOPS and 3 gigabytes of read bandwidth. So what we see with RocksDB is that it's within 2% of the direct attach performance. That is, if you take these SSDs and stick it into the same device and run RocksDB, you're within 2% of that. Okay? The magic, of course, is right here. You see, this is the disk bandwidth over time on the target side. And what you're going to see is these, as RocksDB does compaction and things like that, the bandwidth of the device is going to jump to about 3 gigabytes often. When you try doing this with SATA, you're going to have a lot of other unwanted effects because that won't reach to 3 gigabytes per second. It's a lot of it. So it's good. And then we have to look at latency, because latency is the problem that gets introduced when you move something over the network. And we drew out the CDF, and essentially again we see about a 2% difference. This little gray thing is the DAS performance, and this is the NVMe-over-Fabrics. And there's a slight increase in tail. There's an average slight increase in average latency, but overall we see that you're running this over the network and you're still tracking DAS performance. So basically you're building a remote DAS technology. And the CPU utilization on the host is about, overhead is about 10%.
Aren't those read latencies awfully high?
Yes, but you remember running the RocksDB stack. So once RocksDB starts doing, yeah, it's through RocksDB. It's not just a FIO stack. Now RocksDB is doing all its fancy B3 LSM stuff, and it's doing compaction and all those things. So then we'll take a look at TPCC, which in my opinion is what many, not in my opinion, it's a real world application that's a benchmark that I think everybody is using. And so we're running MySQL version 5, some of the later version. We're running a pretty big TPCC 500 warehouse setup and 150 connections or so. And this is how we ran it. That is, we have multiple, we have the NVMe-over-Fabrics target, and it will have a bunch of SSDs. We'll divide up the target into data directory and log directory, because MySQL has two kinds of writes. The log are a bunch of sequential writes, and the data maintains the database. And then we'll start copying these Docker instances to start adding more and more traffic to the same NVMe-over-Fabrics target until it keels over, basically. And or we try to make it keel over. And that's the basic setup. And this is how that looks. So we have the target server is a Skylake class server with about 8 NVMe SSDs connected over 200 gigabit NICs over to a top of rack switch. And then we have an N number of MySQL servers connected over Ethernet to a bunch of clients driving the traffic. And what does the performance look like? So that's TPMC's transactions per minute for the C workload. And what you're going to see is DAS. How did we run DAS? And DAS basically is direct attached. So as we scale the number of TPCC instances in DAS, we're going to stamp another copy of the whole machine. So we have a machine X. We had some configuration. We got 250K TPMC. In order to scale DAS, you have to add the whole thing again. So it's a linear thing. You're just adding lots of resources to, you're just duplicating everything, storage, compute, memory, to get that blue line over there. So NVMe-over-Fabrics is the red line, and iSCSI is the green line. And so what you're seeing is, as you go up, as you add MySQL instances, either by adding it to the same client or stamping another client, you're going to keep scaling your TPMC as you go along. And since the primary traffic is I/O, what I'm trying to show is that the NVMe-over-Fabrics target is able to deal with additional, as you add additional instances, is able to continue to perform. And this is when your NVMe devices are starting to shine here. If you had put some other kinds of devices like SATA devices, it wouldn't scale at all.
Do you happen to know what the latency of the transaction is as you add more?
Latency of the transaction, we can measure that, but it's transactions per minute. So the actual number is transactions per minute. So it is tracking, and on average it's fine. But you're asking, like, is there over time is each transaction starting to take longer?
So what I'm asking is that when you're adding more instances, right? So throughput might be scaling pretty much linearly. What happens to each transaction now? Is the transaction...
Yeah, I know over time is each transaction taking longer to do.
So if you use Sysbench or something, it gives you like 95%.
Yeah, it is not going up by much. I know that because if the latency was going up a lot, then this would be further down. Right, but I can get that number. It's not that hard.
That's necessary. Yeah, that's not true. That's not necessary.
Not necessarily true, but I would expect.
It would be nice to add the average in the 95th percentile of latency.
Yeah, we can add that. Yeah, it will be done. Correct. So the other thing that we need to look at is, does NVMe-over-Fabrics add how much CPU utilization when you're running the stack on both sides? On the target side, we are not running anything except the NVMe-over-Fabrics stack, right? It's just a block device coming out. On the other side, we're running the actual transactions, right? So that MySQL is running, so that's fully utilized. And you can see that the compute on the target side, even while driving 2-3 million transactions per minute, is still about 25%. There's a lot of oomph still left in this thing. That's why I don't think there's a big latency effect. Sure, but there's nothing happening in the network here except for those things, right? I mean, this is an over-provisioned 100 gigabit switch over there. It's like there's nothing going on over there.
Do you know what the reason is for the little bit of divergence between the blue and the red?
Yeah, it's a 10 microsecond. That's one of the components is the 10 microseconds overhead, right?
I think he's asking for the increase in divergence. It's not truly parallel. It's starting to reduce over time.
Yeah, I think that could be part of what other person is talking about. That is like as you add more and more load, you are adding a little bit, right? And that's why it's diverging a little bit. So yes, it would be great to get that number. I agree. I totally agree that I should have another chart. I should have another chart that shows that. Okay. So the next thing we look at on the storage side, what's happening. In this one I was trying to show that if you were to, so here I'm having the number of the drives themselves. Like how many drives do I have on the target side? Now what happened to TPMC over there? So what that is trying to show is, of course, if you just, in the DAS case, you would add a data drive and a log drive every time you try to add another compute. But on the, when you have on the NVMe-over-Fabrics drive, we're going to like about 2 drives before we use up 2 drives, and you can get like more performance, and then you got to add another drive to go up. So we are saturating 2 to 3 drives as you keep adding instances. So each drive handles multiple instances. Basically, that's the point. And so you can get to the same level of performance with much fewer drops. That's sort of the point I was trying to make. So basically, we're using the 750K IOP capability of the device before we need to scale and add another device into the same system. That's the point of that. And then, of course, if you look at and then there are 2 kinds of drives in this box. The drives are the same. There are 2 kinds of targets. One is a log writer, which is just doing writes, the log writes, and the other one is the actual transactions. And so both of them, as you can see, basically claim, just not scale linearly, but nicely scales as I would like them to. Basically, as you add the number of instances, you start using more and more of that bandwidth. And that's what I want to see in a disaggregated storage box.
So those drives have twice the load as the direct attach drive, basically. You're healing up twice as much I/O.
Which one, these guys?
The one in the top left. The first one you described.
Yeah. So you're talking about these boxes, right? Mm-hmm. Yeah. So we are basically running, we take 2 instances and they can run on 2 drives. So if you go back, so here I'm scaling the number of instances. And each instance needs a destination. So I'm running multiple instances to the same destination.
So that the latency thing,
yes,
that should come out.
Yeah. Okay.
So looking at the top right-hand side, we're seeing, we're hitting about 3 gigabytes per second.
It's per disk.
Yeah. And these are drives you can do at least that per drive.
Yeah.
The drives are not actually being overly taxed
No.
on a per drive basis. I mean, the drives are actually in a pretty happy place. I think.
Drives are in a happy place, and we could potentially add, because the CPU is still not utilized, we could potentially add more stuff in there. I just don't have that many clients to keep adding.
Yeah. But it's not, the drives are not the stressor, they're not being stressed at all.
That's right. This is actually an important point. If you had a SATA drive or a SAS drive or something like that, your drives would be running at max now, right? SATA is about, so you have to think about other solutions there. So then that's not enough. TPCC is just one thing, right? We got to see the edges of the performance. So we pick up Sysbench, and Sysbench is a MySQL synthetic benchmark generator, right? So we can run 45% read and 55% write and 65% read and 35% write and 80% read and 20% write, and then we can see the same curves that we saw before. See what happens, and again, the blue line is the DAS line that you would just add the whole thing, stamp another box, and keep going. But you do see that as the amount of writes go up. Remember, our devices actually have 750K read IOPS and only 120K write IOPS. So that's what's showing up here. You're starting to saturate the write performance of these drives. Not just write performance. When you mix it up, the drives have a lower performance, right? You have a mixed useless, and that's what is trying to come out over here. As you add the writes, you're starting to the disaggregated storage is not working as well as you would think, but because it's disaggregated, nothing prevents you from adding another drive or a better drive that has better write performance in case your application is write dominated. But that's the basic point, is we're using very much fewer disks, 8 data and 8 log disks in the blue case, and in these cases you're going to be using only 4 data and 2 log disks because we are sharing all the disks when they're running over NVMe-over-Fabrics. Target CPU, what's the target CPU? Worst case, you get it about 30%. The CPU is still completely available for you to do other stuff. And there is other stuff people want to do on the target, right? We're not doing any of that stuff. The stuff is compression and all these fancy things that you can do. You have a lot of CPU left over to do that if you wanted to do that. I think this doesn't say anything else. It sort of says the same thing. The read bandwidth and the write bandwidth across the three read-write configurations. We are basically efficiently utilizing the disk bandwidth that is delivered by NVMe-over-Fabrics. And so if you need more, you can add more. If you want a write dominated, you could mix and match drives now in your target to have write optimized drives for log and so on and so forth. All these things now become design choices as you build your disaggregated storage box. So, in a sense, what the whole point of this was to showcase that the NVMe-over-Fabrics ecosystem is maturing fast. The industry has work to get drivers ready, operating systems. Now all the drivers, I didn't do any fancy driver stuff. It's just what's available in Linux 4.9. And the high-speed networks are here, our DMA hardware is here. And so basically all we need is to make sure that we can port our applications and they all work. Top level conclusions, NVMe-over-Fabrics reduces remote overhead storage to bare minimum. That is basically you can take your direct attached storage, stick it on the other side of the network, and you still get the performance of the direct attached storage with a slight minor overhead. And that will then, and in addition to that, you have very low, the stack itself doesn't impose a penalty, a big penalty, either on the target side or on the host side. And so basically you have all the components that help you disaggregate the storage. And if you look at data centers, and other things, how they want to scale their compute and storage, and how these are not actually balanced for different applications. This presents, you now have all the components of an architecture that helps you scale all these things independently. And for us as SSD vendors, it has created an architecture where I can build faster and faster devices, and applications can then take advantages of these fast devices. For the last 5-6 years, we have had NVMe devices, and when we talk to customers, it's like, oh, that's great, but SATA works just fine. So and so we're trying to move the industry towards NVMe and NVMe-over-Fabrics technology. This didn't happen in isolation. If you're not there, you should be there. If you care about this, that's nvmexpress.org, and that's me. I'll take questions. Yes.
Very nice work. Nice to see so much measurement and technical gathering. There's a couple of neat points people can pick on, but I think this work is great. Thank you very much for doing it and for making it public. How did you present the namespaces on the PCIe devices to the SQL layer? Was it one namespace per PCIe device that was then just one-to-one mapped out to the fabrics?
Namespace, no. So, I wouldn't call it a namespace. It's not the NVMe namespace. So it's basically one old namespace, one device on the target becomes one block device on the other side,
so just
right?
One-to-one.
It's a one-to-one. But then we can then put a file system on it and then use multiple instances to use the same thing.
Understood.
That's what.
But we can also use SRIO on PCIe.
Yes, we can. We can. Those are all TBD, right? As we get SRIOV devices, there are not too many of them out there. As we get SRIOV devices, we can enable that, and we might see more latency benefits.
So is the advantage of, so what we can achieve through namespace can also be achieved through SRIO?
Yes, slightly different things.
But which one is better from?
I would say from the usability point of view, namespaces are much easier.
I mean, they're two different things, right?
Yeah, they're two different things.
I got 4 terabytes, and I'm going to expose it as 2 terabyte namespaces.
Or you can.
SRIV is a quality of service thing, saying this VM is going to get priority or the same fairness as this other VM to whatever namespace you present.
Yeah.
So it's kind of carving up the.
It's a slightly different way, but yes. From a storage perspective, just namespace. If our device have 2 namespaces, we can expose 2 namespaces on the other side.
In the cases where the devices are actually shared, what do you anticipate in the way of QoS mechanisms just to make sure that noisy neighbors don't become too noisy?
That's a challenge for all the SSD manufacturers. There's lots of work going on in there. But having said that, right now, their noisy neighbor. When you have 750K IOPS and you're only using 200 of it, you add another 200, there's not too much noisy neighbor yet. But this technology will make the noisy neighbor problem worse, and we're going to have to solve that problem.
You think that existing work with NVM sets and screens and identifying and at that level of granularity is the right path?
It is one of the good paths.
Yeah.
You're asking me guys to sense.
It is one of the good paths. It's one of the good paths. Wasn't that politically correct?
That's well said.
Any other questions? All right, thank you. Thanks for being a good audience.